sounds clear, and recording is started, so all the boxes are checked. All right, now, so as I mentioned, we are going to use energy methods to calculate the deflection in beam, truss, and frame. So that's the methods that we're going to learn today. Here we are in the halfway through. We complete all these 6 weeks, so 50% job is completed. 50% is remaining. This Thursday, assignment 1 is due, so please complete your assignment if you have any remaining questions. All the topics that we have it on, all the questions in the assignments can be solved using the previous lectures and workshops. As you know, every week we have 1 questions from each week, so you can smoothly finish it off that examples. In case if you have any questions, you can send us an email. I also issue assignment number 2. You can check on LMS. You can find assignment number 2 in the assignment folders. Again, every week you have 1 examples to complete from the assignment 2. This week, when you finish the energy methods, you can take the questions 1 from assignment number 2. So during the mid-semester break, you can even complete assignment 2 questions 1. Next week, we don't have any lectures and workshops. We have a mid-semester break, so we don't run any lectures and workshop during the mid-semester break, of course. But if you have any questions, you can more than welcome to send an email, and we can answer any questions. I generally suggest students to have this mid-semester break as a catch-up break, because you might have some study to catch up during this week to catch up all the 7 weeks of work. So please use that week effectively. All right. These lectures will introduce the energy methods. The name energy methods also has some meaning out of it. So I will talk about why they call energy methods. To calculate the displacement of the truss and beams. It can also use in the frames. In our subjects, we are not dealing with the displacement of the frame, but these methods is very powerful. This method is very powerful, meaning these methods are used to find the deflections in most of the structure members. You remember that we also have a similar method. Similar method means we learned one methods called elastic curve methods. You remember these methods? In which we learn elastic one, deflection of beam elastic in week number 5. What happens in that one? So students may ask that we already know one method, which is the elastic curve methods, dA m over ey, and you integrate once, you get the slope, and you integrate again, you get the deflections. Was good, right? Why do you ask us to learn one more methods to find a deflection? Look, this method has the limitations. What is the limitations? Because these methods can use only for beams. You have not come across in week number 5 any truss deflections or frame deflections. So this method has the limitations, right? We can't just learn only one kind of a members, which is beam or truss or frames. We need the methods which can be applied to all kind of a structure. So this energy method step in. It's very powerful method, saying that it can be used in the beams, frames, and truss. So that's the one important things that we want to see. And this week only we're not talking about bending moment diagrams, shear force diagrams, or support reactions would be there, but we just going to calculate the deflections here. We are interested in deflections. And what is the importance of deflections? Where do we use deflections? Look, deflection is not a quantity or not a parameter that will recognize the failure of the structures. Like when you have a beam, let's say I am sitting on this beam. Let's say I'm sitting on the chair right now, and I'm sitting on the beam. So this beam under the load, it will deflect at some amount, right? But this deflection does not meaning going to tell that beam going to fail or not going to fail. You can't tell by from this quantity saying that it's deflection too much, meaning that it's failed. There is no rules in the structure design and structure analysis saying that By looking at the deflection, you can say that the beam is fail and not fail. Yes, bending moment and shear force can be used to check whether the beam is safe or not safe. But for deflections, this is not a case. So that is a good part, that in this quantity, we are not dealing with something that structure is going to fail. The life is not at the risk. But where do we use these displacements? Now the displacements generally used in the serviceability. The word serviceability used in the design. That serviceability meaning that your structure should be serviceable. Meaning that you can design the structure safe. Meaning that okay, if the users using your structures, beams, slabs, it is safe. It's not failing. It's okay. But if it is deflecting too much, vibrating too much, the users of that buildings not able to use that service or not able to use that buildings because it's not serviceable. So we need to make sure that the structures are safe and serviceable. So this deflection comes in the serviceable, because you don't want to design something that is just jumping up and down all the times when you walk it, right? You don't want to design that. That's the comfortness of the users. That's the displacement. This week is just wants to make it comfortable. So our users and all make it comfortable. They don't feel vibrating and jumping up and down. Okay, so that's and Australian standards telling us some limit, that what limit that we're going to use it. So Australian standards telling me that if you know this length over 250, that's the allowable deflections in the beam. Then you calculate a deflection using these methods. And if it is comes under, let's say you calculate this delta using these methods. If delta less than L over 250, then we okay. Our users are okay. So that's how we use. So our job right now to calculate this displacement in the structures. Next semesters, we're going to compare this displacement with the Australian standards to making sure that our structures are serviceable. So that's where we are standing right now. So this week's let's give you the concept of external work and strain energy. Probably you have heard about the concept of energy in the physics. I will revise that one. Then we're going to talk about principle of work and energy. Very powerful measure, virtual work methods. That's I'm going to introduce. And then we take some examples and we summarize in 2 hours times from now. Generally, let's say we want to have an external work. You know what is work? What is work? Work is done by the force defined by the distance from delta x multiplied. Now basically what is work? Work is something that you have an object and you are pushing, you have a chair, let's say your chair, and you are pushing the chair. So if you are pushing the chairs from one end to another end, then you are applying the force. And that force times the distance is called work. Do you understand that, right? So if I put quantity is called external work, right? It's an external work done by external. And what is that? Force. Let's say this gentleman wants to pull this box from this end to this end. That is the displacement, right? This is the original position and this is the final positions. Original to final. So that is the distance times by the amount of force required to move from this original position to the final positions. Now please look at that. This gentleman is pulling in these directions, but we can't use that force. As I mentioned, so definition saying that we need to have a force going in the same direction as the displacement is going. So we need to have a horizontal component of this force times by this displacement. That will give you the external work done. So I hope you understand that. Now don't be worried about this calculus, because student may ask that okay, that looks very simple, that force times displacements and the force should be in the direction of the displacement. What is happen about this integration and calculus? So this is making that let's say if you have a very small distance dx, which is a displacement, you take it very small displacements, like a tiny bit of displacements dx. Then if you just use the summation, this integration is the addition. So dx, tiny dx, tiny dx, tiny dx, tiny dx, you have million dx, or billion dx or trillion dx. from this original to another. So you need to sum them all up to get this final work. So therefore it says that from original to final, that is the summations of all your dx. Okay, and this is force times displacement. That is the calculus. The integration is just a summation. It's just addition of small quantities. Okay, so that is the calculus. So I hope you understand the external work done. Now unit of external work done is joule, is a Newton times meter, and then also represented as a joule. So if the force is a constant, then you will have P times delta. Is saying that, let's say you have this rod like this pen and you are pulling that pen like this, and the one end is holding and I'm pulling it, that is the force P, then this will extend by some delta. So that's external work is the load in the direction of displacement times by the displacement. So that is here, the area. Now in another case, let's say you want to have a force which is increased linearly. So I use the same pen and there is a zero force. I'm not pulling it right now. I'm not holding it. Then I start pulling it slowly. So I start pulling it slowly, then it will displace a bit. Then I start pulling again some more, it will displace. Pulling some more, displace, and finally I pull it up to load P. So then you will have this line, right? And that the area under that line will give you that external work done. That is basically your 0 to delta, right? 0 to delta integration, 0 to delta will give you this area, right? Basically that is the area under the curve. The integration also telling me that the line or curve, the area under the line and curve can be found by the integration. So this is the external work done. In the case of when the load is increasing linearly, you have 1/2 P delta. Where is the 1/2 P delta coming from? This 1/2 P delta coming from this area under this triangle. If I have this 1/2 base times height, which is 1/2, base is delta and height is P, right? So 1/2 P delta. So that's the just the external work done. Now the same thing, same concept can be applied for moment. Like force and displacements, moment and rotation. So if you have your car wheels and you want to open the nuts in the car wheels, you have these spanners that can have a force to open these spanners with some rotation theta. So that same concept, moment times very small delta theta d theta, very small rotation, and you want to add up all these million d theta rotations, and then there is an integration. So moment times is again, this is external work done. If you have a beam, again the beam has a moment, and this moment will linearly increase. There is 0 moment at the start, and then you slightly increasing these moments little by little, then the rotations will be increased as well as respective moment increase. In that case, the area under this triangle is 1/2 times base times height. So 1/2 times theta times m0, that will give you this external work done. Is exactly the same concept like in the last slide, where you have a load and displacements. Load is increasing linearly. You have 1/2 times load times displacement. Similarly, you have a moment in the beam. This moment increasing from 0 to some value of m0, and then there is a respective del theta, which is a rotations. Therefore, we have 1/2 m0 theta, right? So it's exactly the same work concept that we just saw. All right, now you understand external work done. External work done, I have a box, I'm pulling the box from outside, 1/2 or P times delta, load times displacement. Load should be in the same direction. External work done, good. Moment times theta, yes, can be done. External work done. Newton times millimeters, that's the unit, and joule. So that's chapter is okay, the external work done. Now I want to give you the another one called internal energy. What is internal energy? The another name is also called strain energy. Okay, is the energy stored in the body caused by the external work done and or external force. So what happened here? So when you when you press something, when you pull something, so these external work done will be converted into the internal work done, because it need to be balanced, right? External work done should be internal work done. So there is something happen internally. It's not everything happen externally, right? When you do something outside, something happen inside as well. So that's inside happening is called internal energy. Everyone understand that? So when you pull your boxes from one end to another on, there is an internal energy stored in the body as well. That internal energy converted into kinetic energy, and that's how the object is moving, right? So that's how the internal energy help to move. So external work and all this internal work need to work together. So everyone clear for the external, but let's talk about the internal work done. Now, when you talk about the internal work done, we are like in the external work done, you have load and displacements, right? So similarly, we have a quantity, because in external work done, we have load and we have displacement, right? In here, what in internally, we need to divide this load by area, right? Because the internal energy should be stored in amount of how much area is there, right? If you have a big box, small pen, big pen, and so on. So you have a energy stored internally depending on how much area is there. That load over area, that is called stress, right? You know that, right? So internal quantity is a stress, which is the external force divided by area, right? So that's stress. You remember in the last slides, we put load on the x-axis. Load, then we divide by area, because we want to see how much energy is stored. So that's stress, load over area. Now strain, we put displacement here on the x-axis. Same thing, we will just put the strain, but we want to know what was the original length. So that is the strain, change in length over original length, delta. So that is your strain. So basically, when I have this pen and when I apply this load, which is here, when I apply this load on this area of that pen, is the stress, load over area. But when I pull it, that is the original length of the pen. When I pull it, that is some extra quantity, that is delta, divided by original, which is a strain. So that is the internal quantity, because we want to refer back to our original value. So therefore we have this P over delta. So still fine, same concept. Internal work is equal to 1/2, that is the area here again, 1/2 stress, strain, and dV. dV is a volume, the quantity, this very small volume. Then you take a very small volume and you take a million volume over this whole volume, then you can calculate those those things. Okay, so I hope you understand. The definition are still holding the same, that load times displacement, but here in the internal quantity we are just talking about these external internal quantity, stress over stress times strain. Now what happens here, we keep it stress as it is, and with the strain, you know the Young modulus is equal to, I think, the stress over strain is basically this line, slope. So this distance, which is your stress, divided by this distance, will give you the slope, the angle. That is your Young modulus. That's Young modulus. If I want to make this strain as a subject, then stress over Young modulus. So if I replace this one by stress over Young modulus, you get double stress, stress square over 2EA. So I'm just changing this guy to stress over E, right? So that's, I get it. Now strain energy for truss, then sigma square 2E. Now sigma, as I mentioned, that is a load. I think they are just putting n here now. So that is n square a square. So that is n square a square and 2E. And then you can have just the length, then n square L over 2E. Okay, so that is just the internal energy for the truss members. That's the equations. If you have internal energy in the beam, you have basically this is the axial stress. When you pull the members, in this direction is an axial stress, either compression or tensions. If you bend the members, if you bend the members like this, then it's called bending stress. When you pull the members, is the axial stress. Axial stress is equal to how much load I am applying over the cross sections. That is the axial stress. That is done in the truss members. It's just the axial stresses. The truss member don't have any bending moment, so therefore we have this load over area. But in this beam, this is a bending stress. Bending stress meaning that if you bend something, let me get that other one. This one better. All right. So if you bend, instead of these N over A, we have My over I, which is the moment that I am applying. Here, bending moments, distance where I want to find, and if you just do these integrations, you will find this internal energy in the beam. All right, let's take an examples here that calculate the strain energy of the truss systems, and we have equations. N square L over 2A, N square L over 2A. That is the equations for calculating the internal energy. Right. What is N? N is the forces, internal forces in the member. L is the length of the members. EA called axial stiffness. Axial stiffness means how stiff it is, right? Like for examples, so that is EA. So now we have three members, so we can have a N1 L1 square over 2EA plus, let me write it here, N1 square L1 square over 2EA plus N2 square L2 square over 2EA plus N3 L3 square over 2EA. Okay, so there are three members. If it is 4 or 5 members, you can continue tick writing it up. EA is constant. There is EA, they don't have different values, otherwise you can substitute different value for EA. You can calculate the internal forces. You know how to calculate the internal forces. You can calculate the reaction, and you use the joint methods to calculate this 500 Newton tension force, 500 Newton tension force, 775 compression force. So you substitute those values. Let's say N1 is, let's say this is N1. Let's say this is N2 and this is N3. So you substitute N1, length is 2 meters, L1 over 2EA. N2 here 500 square times 2A, and this one compression is a minus, so square, and the length is 2.82 over 2A. You got this. Okay, so that is the internal. Very simple. Equations given. You can just calculate the internal forces times by the length, internal force square times length over 2A. You unmute yourself if you don't understand to calculate the internal energy in the truss systems. If someone says that what is the internal energy in the truss systems, and by the way, what is the internal energy? Is the energy stored in the truss systems due to the external loading, 500 newtons in this case. So that is the internal energy. Unit is Newton. No, unit is Joule. So that is simple. How to calculate the internal energy? There is very simple equations, and then that can be used. All right, for the beams, and if you want to calculate the truss, we can have a same equations here, m square over 2EI. So m square over 2EI, and if you make a cut here at a distance of x, then this moment that you are applying, that is load times distance x. So moment is equal to minus px, right? So that you substitute here over 2EI. You can take the common out, x square over PL. So I can just do a little bit of work here. That is s cubed on 3, 0 to L. So p square on 2EI, L cubed on 3 minus 0. So that finally you get p square on 2EI times by L cube. Now, by the way, this EI is a axial, no, flexural stiffness. Flexural stiffness meaning how. All right. All right. So now you understand the external work separately and you understand the internal work separately. If someone asks you, can you calculate the external work? You can show what is load and what is displacement. You can calculate Joule external work. Internal energy or strain energy you can calculate. We have taken two examples, truss and beams. And you can calculate the internal energy separately. Two different quantities connected together. Now there is a word called principle of work and energy, and that is a new word coming, conservation of energy. What is conservation of energy? State that work done by the external force is transformed into internal work done in the body. It meaning saying that whatever you are applying externally, you are, let's say, pulling the box in the directions, then the same, so you done the work, so the same amount of energy, so if you have an external work, you have same amount of internal work is stored in the body. That's what the conservation of energy say. So whatever you do external should be equal to internal. So the saying that external work done should be equal to internal work done. So I hope you understand the two quantities. We have taken two separate quantities. Now we are saying that if you are doing this conservation of energy business, you need to have this external work done should be internal work done. So that's all good. So in that case, if I have a truss system and someone telling me, hey Vipul, can you please find me this delta displacements? Because if I'm sitting here on the truss, or if I am driving on the car, or if I'm standing here, this truss should be have some deflection. Can you tell me what is that deflections where you are standing with the load P? Yes, we can use this method saying external work 1/2 P delta, right? You know, you remember from my last slides, right, that you have 1/2 P delta displacements. That is external work. Internal work, you again remember N square L over 2EA. And there are how many? 1, 2, 3, 4, 5, 6, 7, whatever that you have N1, N2, N3, and so on. So you are in the positions to calculate the calculate those quantity. Load knows, because I am sitting here, I know my weight, so I can see what is the load there. You know how to calculate based on this load. You know how to calculate the internal forces in the each members. Length of the members, you know what materials is made of, what the cross sections is there, you know that one. So you can calculate delta because you know all the quantity except this displacement. So it's very powerful methods. You can see here that if you know external work and if you know the internal work, you can calculate the displacement, because the displacement, the quantity which is unknown. Simple. If you have a beam, again, let's say I'm sitting on my chair very nicely here. I'm applying, let's say I'm 70 kilograms, then times by 10, that much Newton. Let's say 700 Newtons I'm applying here. When I apply 700 Newtons, the beam will deflect slightly, right? So that beam deflections need to be calculated. So again, 1/2 P delta external work that we explained. That is the equations for moments. You remember that in the last slides we have done these examples to calculate that one. EI we know moments. You can take the internal moments and you are able to solve these displacements, or you can solve these rotations, right? Using this external work and same internal work. So you can solve for theta. Very simple, right? It's not that difficult like in the elastic, and you can see they can apply in the truss, they can apply in the beam as well. You remember here in this week number 5, you remember that d square y on dx square is equal to m over ei. It was quite long to get the rotation and displacements, and it's only used in the beam. You cannot use in the truss. You can use the elastic curve methods in this truss. No, we can't use it in truss here. We can't use it, right? Because there is no such things. There is no moment here, m square ei. So we have this d square y on dx square is equal to m over ei. Was elastic curve equations that was complex, right? So we can easily find the displacement using this energy conservation matters, but we have a problems. Let's just take an example and then we discuss the problem. So we have a same truss. You remember the truss that we take in the example number 1. We have same truss. We have asked to calculate this delta when someone pulling by 500 newtons. So this will find 1/2 P deltas is the external work. This is the internal work. External work is 500 newtons. Delta we need to find, divide by 2, and we found these quantities, right? This quantity we found. So you can just multiply by 2 divided by 500. You get these displacements, right? 4820. So very simple to find the displacement in the truss systems, right? External work equal to internal work. You can find external work, you can find internal work, and you can find the displacements. Same examples like we done it in example number 2. We can calculate the external work 1/2 P delta. And we also calculate the internal work. So if you just make it together, 1/2 P delta equal to P square L cubed on 6 EI. Then you just times by 2 and then times by P, or divide by P, sorry. So 2 divided by P. So these cancel. We have P. So we have 2 and 3 cancel. So PL cubed on 3 EI, as you can see here. So it's very simple. As you can see, if you do the double integration methods here or elastic methods, d square y on dx square is equal to m over EI. Then you do the integration, then you do theta, you do V, and then you get C1 and C2, you get C3 and C4, and then you do the boundary conditions to calculate those constant, and then you substitute back. So it's a quite long process here. Within I would say less than 5 minutes you will get your answers. In here elastic curve methods you might take half an hour to solve the whole process, right? So very powerful methods, as you can see. In elastic curve methods we need a long time to solve this one. Here you have external work, internal work, and then if you just equal both external work, internal work, and you can extract those quantities. Similarly, we can find the rotation as well. External work is moment times the rotation half, and you can again calculate this internal energy. If you just make it equal both, and you can find those theta values. Now we have a problems. What's the problems? That in the previous methods meaning in here. In here, what's the problems? The problem is when I apply the load, I can find the displacement delta at the point where I am applying the load. Do you get me? These methods can only use to find the displacements where you are applying the load. You cannot find the displacements here. Ooh, you did not tell me that, right? But you look at the examples. Look at here. We find the displacements here. We did not find the displacement anywhere else. We find the displacements where we apply the load, right? We did not find the displacements, or we did not ask you that displacement, finding the displacements where the load is not applied. So there is a big limitations for that. It was easy, was nice and smooth to explain. It can be applied for beam, it can be applied for truss, even it can be applied for frame. Was very good methods 1 and 2. I like it that matters as well. But the big limitations for this one is that it can only and only use to find the displacements where the load is applied. You got my point? So these methods 1 and 2 that I just explained in first 42 minutes, it cannot be used in most of the places, because you not always tend to find the displacements where the loads are applied. You Someone might come in your office when you are engineers and you might say, I know one methods, but you need to tell me but I can find the displacements only where you're going to sit down, right? If someone sitting here, let's say I'm sitting here with my chair, I can find a displacement here as well. If you are sitting here and if you tell me to find the displacement here, I can't do it. I don't want to feel that way. I want you to introduce you to new methods where regardless where you sit on your beam, you can find the displacement. So the new methods, it is called virtual work methods. The concept is still same. Please note the methods which I teach you in the last 43 minutes does not change. We are going to use the same concept, the same philosophy, I would say, or same definition, but we will change a slight a bit to find this displacement concept. So we call it principle of virtual work, or we call it unit methods. We call it energy method for deflection. There are multiple names. By the way, these methods are developed, I think, in 1770. I think let me find that details for you. Okay, I found it. So this method is quite old. This method is quite old. Methods is found in 1717. You can say almost 300 years ago. And John Bernoulli, that's inventor of these new methods. Very powerful methods, by the way. I like teaching these methods, virtual work methods, because it's very powerful. 300 years ago, still we are teaching this one. So let's say principle of virtual work, PVW, which is a PVNW, it's a short name, based on conservation of energy principles. As you know, external work equal to internal work, that is the energy conservations. So virtual work is the work done by the virtual force acting to the real system. So what we are doing it right now, what is we doing? That someone saying that, can you please find the displacements where, let's say this is a body. It could be beam, it could be truss, it could be frame, and it has some supports. It has some supports here, which is fixed. If you don't put supports, this just keep going in the space. So in that case, if I want to find the displacement at the point where the loads are not applied, like look at the load P1 is applying here, load P2 is applying here, load P3 is applying here. So our job is to find the displacement at point A where the loads are not applying. That's good, no problem. So the virtual work method saying that you put the dummy load. Dummy load meaning dummy load meaning this load is virtual. You can call it whatever you like, not real, virtual, dummy, is not there, whatever you like. So you put the load where you want to find the displacement. So that is called virtual systems. And you need to put the load in the directions in which you want to find the displacements. Okay, so you find the load in the displacements and finding the direction in the displacements. Applying virtual force, as I mentioned, there is no rules that you need to apply only one unit load. You can apply 2, 3, 4, 5, but then I will tell you, then you need to divide or multiply by this one. So this is a virtual. So we just generally ask students to put the 1. Okay, at a point in the same direction where the displacement need to be found. So you need to put in the same direction where the displacement need to be found. Now, same thing, external work equal to internal work, right? Same thing, external virtual work, as you know, 1 that we put times the displacements where the external work done is done equal to internal work done, and then we can find these displacements, right? So it's very simple, that not so difficult. So for the truss, as you know, external work, this is by the way virtual work, virtual force times the real displacements times the internal forces times the real forces. So if I just rearrange this one, you have a internal force due to in the virtual system, external force in the virtual system, length and axial stiffness. Please note this virtual force has a no unit. This one has a no unit. Okay, you don't need to put any unit, Newton, kilonewtons or so on. There is no unit for this virtual load. When I take an examples, I think it will be more clear. For the beam, same thing, external work equal to internal work, and we can solve for either displacements or rotations, right? If you want to find the rotations, you need to find the unit moment in the directions of the rotations that you need to find. Okay, so very simple methods. Steps I will not going to show you because once I take an examples, you will know what steps we are taking it. We're going to take an examples here. You remember the same examples, but we're going to solve it using the virtual work methods. So let's solve these examples by writing it. All right, so let's solve these examples by writing it, not just walk you through. So it will give you more kind of insight on that examples. All right, and I will going to show you Excel as well. We can use the Excel sheet to do some. All right, so what we need to do it, we need to use virtual work methods. To find displacement delta at point B. Right, so what is the formula? I think the formula is given here for truss. Here you go. This is the formula. Let me copy that formula for you. So you know where it's coming from. So let's say we want to find this. Okay, so that's the formula. So what we're going to do it, we're going to create the virtual system and real system. So let's do the real system first. So number one, let's draw the real systems. I will explain you these equations as well. Let's do the real systems. The real systems look like is a pin support here, roller support here, and 500 newtons here. And we have 2 meters, square root 4 plus 4 is equal to square root 8. Right, so if I draw the free body diagrams with the reaction forces, we have, let's say, put A, B, and C. Reaction force A, reaction force HA, reaction force C, and we have 500 newtons at B. You have 2 meters, square root 8. Right, so let's find the reactions. So let's say this is A. Sum of the moment at A equal to 0, anti-clockwise is positive. So RC times by 2 meters minus 500 newtons times by 2 meters equal to 0. So RC equal to 1000 Newton millimeters over 2 meters is equal to 500 newtons, right? So that's the RC. Sum of the force in the X direction, left to right, is positive. HA going positive, 500 Newton positive. So HA equal to minus 500 newtons. And sum of the force in the Y direction, upward, is positive. So you have RA plus RC equal to 0. And RC we found 500 newtons. RA equal to minus 500 newtons. So we found all the reaction forces now. Let me put it up. That these RA 500 Newton going down because minus. This is 500 newtons. A, C, this is 500 newtons external force. B, and this is 500 newtons. This is 2 meter, 2 meter, and square root 8. So we can use the joint methods to calculate the internal forces. What happens here? Let's say let's do the joint A. This is A. This is 500 newtons. 500 newtons. Force F AB and force F AC. Let's put the name 1, 2, and 3. Member 1, 2, and 3. So this FAC, FAC equal to 500 newtons tension. FAB is equal to 500 newtons tensions. So AC is 1 because N1, let's put the N1 there, is 500 Newton tension. N2 is 500 Newton tension. And we can use the joint number C. This is 500 newtons. This one 500 newtons. And this one N3, let's say. So 2 square root 8. So N3 vertical component 2 on square root 8 plus 500 newtons equal to 0. So N3 equal to minus 500 newtons times square root 8 on 2. This gives me minus 707 Newton compression. So N3 equal to minus 707 Newton compressions. You can unmute yourself and telling me that which part you don't understand, because sometimes it's no trouble. Okay, so that's all good now. So this is the real system. So in the real system, you have N1 equal to 500 newtons tensions, N2 equal to 500 newtons tensions, N3 equal to 707 Newton compressions. Okay, so that's what we found. Now virtual systems. Now in the virtual systems, what we need to do it, we draw exactly the same truss. Let me get this truss down there. But we remove all the external forces. For the virtual systems, we draw exactly the same truss. This is same truss, 2 meter, 2 meters, square root 8. It is A, B, and C. Sorry, B was here. B and C. And we're going to draw the pin supports, roller support, same. Now we're going to put the virtual load in the direction of the displacement that we need to find. Do you understand this? Very simple. We remove all the external forces and we put the virtual force in the direction of the load that is going. That's where you need to find. If someone asks you to find the displacement in these directions, you need to put the virtual load in these directions. Okay. So and then we're going to find this small n1, small n2, and small n3, which is, by the way, the internal quantity in the virtual systems. So let's do the same thing. Let's draw the free body diagram first. in the virtual system. So this is C, RC, this is RA, this is HA, this is 1. By the way, there is no unit for the virtual load. 2 to square root 8. Sum of the moment at A equal to 0 anti-clockwise is positive. RC times by 2 meters minus 1 times 2 meters equal to 0. So RC equal to minus 2 meters over 2 meters equal to just 1 Newton. So RC equal to 1 newtons. Sum of the force in the x direction left to right is positive. 1 minus HA equal to 0. So HA equal to 1 newtons. And then you have sum of the force in the y direction upward is positive. RA plus RC equal to 0. And RC is 1. So RA equal to minus 1 newtons. Right, so we find all the reaction forces. Let's put it in the free body diagrams. That HA is 1 newtons. This is A, this is B, this is C. 2 to square root 8. The C is 1 newtons up. This is 1 newton down, and you have 1 newton going here. So same thing, joint method. We can use joint number A. Joint A, let's put 1, 2, 3. So this is small n1, by the way. Small n1. 1 newton going this way. 1 newton going this way. And this is small n2. By looking at the figures, some of the force in the x direction and some of the force in the y direction, n1 would be 1 newton, n2 would be 1 newtons. Similarly, we can do the joint number C. Which is 1 newton. This is 1 newton. And this one n3, n2 to square root 8. So sum of the force in the y direction, 1 newton going up plus n3 times 2 on square root 8 equal to 0. So n3 equal to minus 1 newton times square root 8 on 2. Is equal to, we can find it, minus 1.41 compressions. Right, so n3, these are in tension, these are in tensor, and minus 1.41, that is compressions. Okay, now we can find the deflections using the equations. Right, what equations that I am talking about? These equations. Let's copy that. Paste. Okay, so delta is equal to small n1, capital N1, L1, E1, A1 plus N2, L2, L2, E2, A2 plus N3, N3, L3 over E3, A3. Where this 3 coming from or 1 coming from? That is, we have a total 3 members. So therefore we have total three different quantities. So let's substitute value n1. We calculate n1, which is 1 newtons. 1 times capital N1. Let's go back and find it. 500. 500. Length L1. Let's put length L1 2 meters over Young modulus is constant. N2 same thing, Young modulus constant. N3 we have a same value, N3 minus 1.41 times by N3 we calculate minus 707 minus 707 times by L3, I think square root 8 over EA. So if you solve all of this, you get 1000 over EA plus 1000 over EA plus, let me use the calculator, 2819.6 over EA. So you get 4819.6 EA as a displacements. Right? You got the points here. Do you understand, or do you it's too fast? We can use the space case for these examples as well. So in here we can just draw the members, let's put 0, enter, and we have 2 meters, and from here we can just draw members, touch it here, and we have 2 meters, and we can close it off. This one, escape key. Then we double click on here because we just want to check what was the robot. So we have these examples. What is? Oh, there you go. So we have a pin support here, roller support here. We have a pin supports, and if you want to show the pin support here, you can just use this one, or roller supports. Here we have roller supports. Then we got what we got here. Then we got 500 newtons going horizontally. So click on here, one click, and go to this node load. Don't change anything. Okay, and in the X direction, force going in the positive, 500 Newton. This is kilonewtons. So be careful with this one. So it would be 0.5 kilonewtons. Because in example it says that 500 newtons, so 500 divided by 1000 give you 0.5 kilonewtons. So you just need to convert 500 newtons into kilonewtons by dividing thousands, and it's in the X direction, left to right is the X direction. So you will see hit OK and hit OK. You will see going from left to right, and if you can't see the force, you can go here, so diagram annotation, and hit OK. And it shows positive 0.5 kilonewton, which is basically 500 newtons. Now we need to put the cross sections area. If you don't, I think in the example it does not show us cross sections area, so we can just put the cross sections area here. Let's put the solid rectangle, solid square, let's say 100 by 100, and hit OK. So we put the cross sections. Let's put the Young modulus 20,000 megapascals, which is, by the way, aluminium. Young modulus in megapascals. Hit OK. And let's run analysis. Linear static analysis. Yep, analysis completed successfully, and you want to, I think, just keep it in the wireframe, and you want to see the displacement. Displacements here. Okay, so in the X direction 0.02 millimeters, right? That's what we want to find. So let's check with our calculations here that I think this is 4819.6 that is in the, I think it's in the meter. So Young modulus, we put 20,000, and the area would be 100 times 100. By the way, this is all in the millimeters. Okay, so let's work it out, and we're gonna change it, because this one, do you remember that we put this one in the meters, this length in the meters, this is in the newtons. So Newton is fine, but meters would not be fine. So let me work it out. 0.6 divided by 20,000. This is, by the way, Newton per millimeter square, 20,000 megapascals, and this is millimeters and this is millimeters, so millimeter square. So this is millimeter square. So 20,000 times by 100 times by 100. So you got 2.40 times by -5, and that is in the meters. So we want in millimeters. So 2.40 times by 10 raised to minus, because this is meter, by the way, times by 1000, that is in millimeters. So you got 0.024 millimeters, which is matched with our solutions, which is matched with our solution, 0.02 meters. And if you want to find in the x directions, you need to repeat the whole procedures here. N1 will not gonna change, but you just put the vertical virtual force. To show you, let's say we will have a, let me put member first. You have AB members, you have BC members, you have AC members, right? These members are shown here. Those are here. Now let me put the small n, and this small n value was here somewhere. We write 1 minus 1.41. So AB 1, BC is minus 1.41, and AC is 1, right? Let me put this one in the some dark color, and let me grab these. Let me grab these examples here. Let me take this example here so we know what we are talking about. Let me put it here. All right. Okay, let's put it here. So this capital N done. Let's put it in the center. Capital N, AB. I think the AB was, I remember that was 500 positive. This one minus 707. I think what we calculated. Let me check. 707 minus. And then your AC is 500 again, right? And the length, let's put in the meter. Length is AB is 2 meters. BC is square root 8. So it's basically 2 square plus 2 square power of 0.5, which is square root, is this 2.82, and this is 2 meters. And here we will have N, capital N, capital L. So we will multiply this 1 times by this times by this, and then we got this here. Let me put the E and A as well. Insert and insert. We don't have E and A, but we assume. Do you remember that? A in millimeter square or meter square, because we have it in meters. So let's put it in the meter square. Was 1000 divided by 1000. That is times by 1000. 100 divided by 1000, because remember you have 100 millimeter. So 100 millimeter divided by thousands give you meters. So that's give you this, and area is same. So that is Young modulus, and the that is area. let's say Young modulus in Newton per meter square. So you have 20,000. So then you just need to convert this one into Newton per, sorry, we need to have 20,000 Newton per millimeter square. So to convert that one, I think I just need to use the, I generally use Newton per millimeter square to Newton per meter square. So I think it's just 20,000. You get 2 times, so you need to multiply this by so you have multiply by 1000, multiply by 1000 to convert into Newton. What happens here? Okay, so that's all good. And this Newtons millimeters divided by EA, so we just need to divide it by this area times by EA, so you will get this, and then sum. I think we just screwed up some these units. I think we just need to multiply this one by 1000, because you remember that was in the millimeter. So 0.024. That's your answers, as you can see there. So you can use the Excel as well. If you have so many values, then you can use the Excel. It will give you the same answers, and that is here. So it's give you almost same answer. So I hope you understand that what we are doing it right now. Please be mindful with the consistency with the units or more details, but I think exactly the same thing. Let me go back and let me go back and do the example here. All right, so what's the questions here? We need to find the vertical displacement at C. All right, so we're going to do the same thing. These are the steps. Real system, and we find let's put N1, N2, N3, and N4. Going to find N2, N3, and N4. We're going to do the virtual systems, and we're going to respectively find small n1, n2, n3, and n4. And then third, we're going to find displacements using small n1, capital N1, L1 over E1 A1 plus N4 L4 over E4 A4. Right, we substitute that value. So that's the deflections at point C. So let's do the real system first. Real system and find N1, N2, N3, and N4. So in the real systems, we have a pin and rollers. Okay, so let's this is kind of a system here. This is the real systems. Let's say this is point D, this is point A, this is point C, this is point B, and the load is applying at point B 100 kilonewtons. Right, and the distance is 2 meter, 2 meter, So this one will be 2 meters as well. So if I have this vertical distance 2 meters, so this is square root 8, same like before, square root 8. So let's work it out for here. Let's redraw these roller supports here. So let's say this is RA and this is pin support. So this is HD and let's say VD. So let's take the sum of the moment at point D equal to 0, anti-clockwise positive. Then RA times by 2 meters minus 100 kilonewtons times by 4 meters equal to 0. So RA equal to 400 kilonewtons times 400 kilonewton meters divide by 2 meters, you got 200 kilonewtons. Sum of the force in the x directions equal to 0, left to right is positive. So HD equal to 0. Sum of the force in the y direction upward is positive. So VD, oh sorry, we have HD would be minus 200 kilonewtons because we have RF force as well. VD going up and minus 100 kilonewtons. So VD equal to 100 kilonewtons. So if I redraw the system here, this is point D, this is point C, this is point A, 100 kilonewton, point B, and VD is going 100 kilonewton up, and HD 200 kilonewtons minus, and RA 200 kilonewton positive, 2 meter, 2 meter, square root 8, 2 meters, right? So what we can start with, we can start with joint number A or joint number B, doesn't make difference. Let's start with joint number A. And by the way, what was the number 1, 2, 3? We're not going to change the number, okay? Virtual system and real system, this numbering would be same. 1, 2, 3, 4. So you have a 1, 2, 3, and 4. This numbering will stay as it is for the virtual and this. So you have 100 kilonewton going down at point B. You have capital N1, you have capital N2, and this would be 2 to square root 8. So sum of the force in the y direction upward is positive, minus 100 kilonewtons plus N2 times 2 on square root 8 equal to 0. So N2 equal to 100 kilonewtons times square root 8 on 2. So let me use my calculator. 100 times square root 8 over 2, you get 141.4 kilonewtons. So that is tensions, and that is N2, and that is positive. So let me put a list somewhere. N1, N2, N3, and N4. And 2 we found 141.4 kilonewton tension. Now sum of the force in the x direction left to right is positive, N1 going negative, and this N2 going negative as well. 2 on square root 8 equal to 0. N2 we substitute this, minus 100 kilonewtons times square root 8 on 2. This is N2 times 2 on square root 8 equal to 0. This cancels. Minus N1 plus 100 kilonewtons equal to 0. So N1 equal to 100 kilonewtons positive. So what happens here? So this minus, this is positive, should be positive. So this would be negative, so that will make it positive. So that would be tensions. 100 kilonewtons tensions. Now we have this 100 kilonewtons coming down, and these two forces we found. Now joint B done. We want to do the joint number A. We done joint. By the way, this is joint B. Now we do joint number A. So joint number A, 200 kilonewtons. 200 kilonewtons going this way. This force is N1, I think. And N1 we found 100 kilonewtons tensions. And this is, I think, N3. Is it N3? Yes, this is N3. So this is again 2 to square root 8. So sum of the force in the y directions, you can't find it in the y direction. Sum of the force in the x directions, left to right, is positive. 200 kilonewtons plus 100 kilonewtons plus N3 times 2 on square root 8 equal to 0. So N3 equal to minus 300 kilonewtons times by square root 8 on 2. It's not matching. What happened here? Oh, that would be minus. So N1 would be minus. Please take a note, because bring this in here. So N1 would be minus, and that would be compressions. So if I have it compressions, then this will goes this way, and that is 100 kilonewtons. Then in that case this would be minus, and in that case minus 100 kilonewtons times by 0.8 divided by 2, you get minus 141.4 kilonewtons compression. N3 minus 141.4 kilonewton compressions. N4, in here we can use the joint number D, and if you use joint number D, is basically 200 kilonewton positive, because you can see this force should be opposite and equal. So positive 200 kilonewtons tension. So N1, N2, N3, N4 done easily. I think week number 3 we done it plenty times. Now we need to draw the virtual system. Now in the virtual system, we are going to find the, let me get these guys here. In the virtual system, let me put it here. So in the virtual systems, we're going to remove all the real loading, and we're going to find the vertical displacement. So you're going to put the vertical virtual load at the point C, and what else? And we're going to put the same numbering, number 1, number 2, number 3, and number 4. So we're going to find small n1, small n2, small n3, and small n4. So small n1, small n2, small n3, and small n4. So let me draw the virtual system for you. So here D, here A. I think we have a VD. We just want to follow the same. Yep, VD and RD, VD and HD, and reactions A. And we have this 1. There is no unit, by the way. 2 meter, 2 meter, square root 8, 2 meters. Okay. And this, there is no force. Please note, we don't need to put the force at B. A, B, C, and D. Okay, so that's the system. Reaction forces, we need to find it. Let me check. Yeah, let's find the reaction forces. Probably we don't need to find the reaction forces here, because look, this joint B has a no load, If there is no load, immediately those guys would have a zero forces, right? So N1 and N2 are zero. N1 and N2 0 straight away, because you can see this joint B has a no load. If there is no load, in that case you don't have any member forces. Then if I use the joint number C, we have this, right? So we need to, this guys is N3, this guys is N, I think this is N2, and that is 0, and that is joint C, and there is a 1 here, and this one is N4. So let's find it. And by the way, this is 2 to square root 8, and this is N4. So let's say sum of the force in the y direction upward is positive, -1 down, minus N3 times 2 on square root 8 equal to 0. N3 equal to -1 times square root 8 on 2. So minus 1.41. So N3 is minus 1.41. Minus 1.41 compressions. N4. N4, let's say sum of the force in the x direction left to right is positive, minus N4 minus N3 times 2 on square root 8 equal to 0. Let's substitute this value. Minus N4 minus 1 times square root 8 on 2 times 2 on square root 8 equal to 0. This cancels. So minus N4 equal to minus 1. So N4 equal to 1. N4 equal to 1 in tensions. Okay, so we got all this value. Now step number 3, we need to find the displacement delta C. Equation is simple. N1 capital N1 L1 E1 A1 plus N2 L2. We have, by the way, 4 members, so we need to write all 4 of them. I hope you understand this simple story that we are following. It's just the 2 examples that we solve, and by looking at this one, you have N1 and N2 0. Look at this, N1 and N2 are 0. So straight away, these guys 0, this guy 0. So the whole thing gets 0. So we don't need to worry about that. N3, small N3, we have minus 1.41. We can substitute that. Capital N3. There you go, minus 141.4. Minus 141.4. L3. L3, let me check. Third number, L3 is square root 8, and that's in the meter. Square root 8 meters, careful with the units. And this E3 A3, I think is given in the examples, is 80,000 kilonewtons. So we got 80,000 kilonewtons plus N4. N4 we got, come on, N3. Oh, we got so far. I think the N4 equal to 1, small N4, and capital N4 is 200. So 1 and 200. So 1 and 200 times by L4. L4 is 2 meter over 20,000 kilonewtons, right? So let's times that up. So that is 7.04 times 10 raised to 3 plus 0.02. I think we just done something that is supposed to not. Right, let me check what we done wrong. So we will have a minus 141 square root 8 over 80,000, and then you have 200 over, oh, that is 80,000, sorry, not 80,000. Okay, that picks up the problem. 200 times 2 divided by 80,000 give you 5 times 10 raised to minus 3 plus 7.04 times 10 raised to minus 3. You get 0.012 meters, because you remember this one we have in meters. So times by 1000 times by 1000, you get 12.04 millimeters. Now I can show you these examples by the Excel, and also I show you by the Space Gas software. Right, so let me go back. Let me put another one. Let's say you have a member. How many members? Okay, let me put back these these guys here, so we know what we're talking about. Yep. So we have member AB, we have member BC, we got member AC, and we got member CD, right? Then we will have small n, capital N, E, and let's put E, let's put A, and then we will have a L, and then we will do small n, capital N, L divided by EA. Right, so let's put these values. AB is in our member 1. AB is member 1, 0, and 1 is 0. Let's put 0 here. Capital N1 is how much? For capital N1 we got minus 100. We got minus 100. Young modulus, and this one we keep it. For member AB we got it 4 meters. 4 meters. BC is number 2, 0 again, and for our capital N2 141.4. 141.4. This one we're going to write, and this BC is square root 8. So 8 to the power of 0.5, you get this, right? Now we got AC. AC is number 3, so minus 141.4, minus 141.4, and this small n we need to find it. Let me put this n for 4, n4 is 200 positive, and small n3 and small n4. Let me go back and put the value there. Small n3 is minus 141, minus 1.41, and this n4 is 1. Length for AC, length for AC is same thing, and length for DC CD 2 meters. Now Young modulus, I think let's assume the area is, let's say, same area, 100 times 100, we got 10,000, and EA we got 80,000. If I want to calculate the Young modulus, I can just say that this EA divided by area, we got, I think this is very small. Young modulus is, we need to get it 20,000. So let's do it another way. Young modulus is 20,000. Then area would be 4. Yeah, that's okay. So now this is dummy, by the way. So let's put 4 and Young modulus 20,000. So that will make it 80,000 EA, right? Because that makes it. Now we can just do this one times this times this, not this one, times this divided by EA. So that's done here, and you can just use the sum function, sum, and we can just select all, and that's in the meter, that's in the meter, and you can just convert this one into millimeter by multiplying 1000, multiplying 1000, that is in millimeters. So I think that's very handy. As you can see, these Excels, engineers generally use Excels to verify all your hand calculations. So you can use the Excels as well. Now I will show you the SpaceCare softwares as well. So we match these SpaceCare softwares calculations as well. So what we got here, let's start with here, 4 meters. So draw members 0 and 4 meters, and then we got 2 meters. I think we just need to make it 2 meters rather than, let's do the new one again, new. So let's turn this one off. Draw members 0, 2 meters, 2 meters, and let's draw another 2 meters. Draw members, and let's draw 2 meters here, and then we just want to connect this, and 2 meters here, and we don't want this one. Let's select this and delete this one, delete. Okay, now we put the pin support here. So Let's put the pin support here. Let's put the roller supports here. Okay, and let's put the cross sections. I think we just done it. I think it's just a 2. I think I'm not sure whether okay it's gonna work or not, but let's see. And then you have Young modulus of 20,000. 20,000 Newton millimeter square, and this one would be millimeter square. So it will not gonna work because you understand that because you have this 20,000 Newton per millimeter square and 4 is millimeter square. So we multiply this by this and it will give you in the Newton only. So you just need to divide it by 1000, so 80. Anyway, let's see. So that's 20,000. Otherwise we just need to, this is in the millimeters. Okay, that is in the Newtons. So that's so you got 80,000 in the Newtons and you divide it by 1000. So this one divided by 1000 give you 80. So you need to multiply by thousands. Multiply by 1000. So you got 80,000. So you have, by the way, this need to be changed. How much was that? 4,000. All right, so that's good. Now I'm just playing with the units. And then once you have this one, you have a load which is which is the 100 kilonewton down minus 100 kilonewton down. Hit OK. Okay, hit OK. And if you want to see that load, you can see this one. So, and we need to find the displacements here. Analysis, linear static analysis. Okay. And then we want to see the displacements. I think there is something wrong. Yep. Bending moment. So here, so axial. I think there is something wrong that I need to fix it, but I think but you got the options there, right? I think you have found that one. I will show it to you in the workshop more example, but I think there is some error that I put the numbers in. Now to complete this example, complete these workshops, let me walk you through these another examples there. So I hope you understand all this one. For the beam is the same thing, that you want to find the vertical displacements at point B. What you do, you put the virtual systems, vertical load and real systems. This is a real virtual system, real system. And for the virtual systems where you want to find the displacements, where you put the unit load, you put small m, and you put in, and then you find these small m value. And for this one, same directions, x distance would be same, and you find this capital M. Once you find this small m and capital M, you substitute the value, integrations, it will give you these displacements value at the point. So it's simple, same thing. Same here. If you want to find the deflection at C, you draw two things. One is the virtual. You remove all the external loading, you put the loading, and you find small m1 and small m2 by making the cut. And then you do the real systems. Again, you find capital M, capital M2. You substitute the value for delta C by M1 and M2, M1, M2, and so on. You can find the displacement delta C. So in summary, I think there are two simple equations that we just come across: N and L over EA. That's a virtual system, real system, and length and Young modulus and area. This is the moments, virtual moments and the real moments. So nothing so complicated. I think in the workshop examples, I will take you more beam examples, because here I just walk you through the beam examples. And also you can use Excels for the truss systems. You can use the space case. I think I will show you the space case softwares again in the beam environment. I did not show you anything. So for the beam, I will show you for in the space case as well.